Hello guys, nice to see you. How are you doing?
Yeah,
Okay, I guess that everyone is here. So we just short. Yeah, good afternoon, everyone. Yes, nice to see you. Um, Today we have our last discussion on gravity, and uh, tomorrow you guys have the second midterm. So don't forget about that and be prepared. So, quick remind of our previous discussion. We introduced the concept of potential gravitational field with quantified potential energy of gravitational field and strengths of gravitational field, which is on the surface of the Earth is considered as G gravitation, like this kind of constant which we use 9.8, but definitely it's not a constant. It's a function of distance from the center of the Earth. We just consider most processes happening on the surface of the Earth. That's why we use it as a constant. We have shown that its strength of gravitational field is a function of distance. Also, potential energy is a function of distance, and we introduced the total mechanical energy of satellite or planetary motion when we have kinetic energy of this motion and also potential energy of because of attractive interaction between two bodies via the gravitational field. So we also have shown that this total mechanical energy is a constant for an isolated system. So we have conservation of total mechanical energy, and that can be used to do certain calculations. So today we will focus mostly on such a concept as escape speed. We will calculate it in two different ways. So first, as we already started last time, we will just repeat from the beginning to make it clear for everyone at which stage we are. And we will use this concept of conservation of total mechanical energy in order to calculate this escape speed. And also we will do it in a more straight, like direct way, derivation via a differential equation, which will relate the change of velocity with its position. And by solving this simple differential equation, we will also be able to derive the equation for this escape speed. So you will see two kind of independent approaches how to do this. This escape speed is quite important parameter because it tells the speed the object should possess in order to leave the planet and never come back. Kind of important for different some reference point for different applications. It will be obvious for you that applying this concept of total mechanical energy conservation is way easier approach to calculate this escape speed. Okay, so now let me change the camera and we can continue. So we stopped last time on the discussion of such a situation when we have a planet with certain radius r. On the surface of this planet, we have some projectile which is launched with initial velocity. Let's call it v initial. And the question was, what will be the height this project can move, and definition of reaching the maximum, the highest point, will be the fact that the velocity is equal to 0, so it stops and either comes back if our initial velocity is smaller than the escape velocity, or it will just freeze in this point or just continue moving if this velocity, initial velocity, is higher than the escape velocity. But at this point, we don't know which is what is the value for this initial velocity. We just want to understand what will be this maximum height. And according to, let's start from simple option. Let's apply previously discussed conservation of total mechanical energy, or this satellite or planetary motion. And we can write the following. So 1/2 times mass of this projectile times its initial velocity square, which stands for, this term stands for kinetic energy initial. Then we have certain potential energy, which is g, gravitational constant, times mass of the planet. Let's not specify that it's Earth, just this capital M will be mass of the planet, and small m will be mass of the projectile. And so we change. So we have mass of the planet multiply mass of the projectile divided by radius of the planet, r, because that's initial position of the body on the surface with respect to the center of the planet. And when we reach maximum, like highest point of the trajectory, kinetic energy will be equal to 0, because we remember this is the condition of maximum height. Velocity will be equal to 0. Then we will have only potential energy, which is equal to g times mass of the planet times mass of the projectile divided by r maximum. So it's maximum distance from the center of the planet, r maximum. And that, so here there's a question, r or r squared. So r squared stands for force, gravitational force, and potential energy, we have just r in the denominator. So we can write this in a bit different form also. will be minus g times mass of the planet times mass of the projectile divided by the sum of the radius of the planet plus this height the projectile moved with respect to the surface of the planet. So now we have this equation. We can write expression for V initial square that will be equal to 2 times G mass of the planet. We cancel out this mass of the projectile here. We don't have it anymore. And that will be times per expression in parentheses, which will be equal to 1 over radius of the planet minus 1 over this maximum distance it will reach from the center of the planet. So now we need to maybe better to express this without second power. We can take square root 2gm 1 over r minus 1 over r maximum. So now we need to consider some specific case we're interested in. So we are interested in the moment when the projectile can leave the planet completely and never come back. That means that it should reach some distance from the center of the planet, this R maximum should approach infinity. So it should just go away from the planet to some infinite distance. And in that case, if we consider that maximum distance is approaching to infinity, then here is 1 over R maximum. So this will approach 1 over R maximum will approach 0. And in that case, the initial velocity, in order to reach this distance approaching to infinity, should be larger or equal to square root of 2g times mass of the planet divided by its radius. So this is the equation which gives us the minimum speed which is required for projectile to leave the planet without taking into account friction in atmosphere, like drag force in atmosphere, and also it doesn't take into account the spinning of the planet or its motion, direction of its motion in the about the sun, because first of all, spinning about its own axis of rotation provides certain velocity vector already at the surface of the planet. That's why space launching sites are usually built closer to equator, and that's actually one of the reasons why Baikonur was built in Kazakhstan, because it's quite south location. Of course, there are other parameters which should be taken into account, like number of sunny days with good weather, also some remoteness of the location. However, one of the important parameters is to be as close to equator as possible in order to gain some additional starting speed because of rotation of the Earth. And also depends in which direction with respect to motion about the sun, this projectile would be launched, or rocket. Because if it goes, the planet, for instance, moves from the right to left, then obviously it will be like require smaller escape velocity in the direction of motion of the planet than in the opposite direction. So all these factors can be definitely taken into account. However, at this point, all of them are neglected, and it's just based on potential energy of gravitational field of the planet, which defines what should be this escape velocity. So this has been done for calculating escape velocity based on the conservation of total mechanical energy. And let us try to do the same based already on more general approach, which involves solving, like building and solving a differential equation. Okay, so, and yeah, let's highlight this part. So remember how it looks is 2g times mass of the planet divided by radius of the planet. So we should get the same result, but with completely different approach. So we have a planet with some radius r, mass m. Also have some projectile moving away from the planet, and there is also from the center of the planet some distance r, which defines position of the projectile. So it probably should be like this. Now we need to recall certain parameters which describe kinematics of motion. We have acceleration, which is first derivative of velocity, dv over dt. We also will need second law of motion, which is F equal to ma. And in our case, since this is isolated system, there is only gravitational force. So here we can write F gravitational, and that should be equal to m times g as a function of r. So m times strength of the mass of the projectile times strength of the gravitational field created in the space around this planet. So we also remember from our previous discussion that this g as a function of r is given as minus g times capital M mass of the planet divided by r squared, which is r is distance from the point where we determine the strength of gravitational field to the center of the planet. Minus stands here because gravitational field is pointed into the center of the planet, so it's attractive force, gravitational force. So now we can write the expression for acceleration, which is actually strength of gravitational field. So let's write dv over dt will be equal to g as a function of r. So instead we put this expression. So it will be minus g times mass of the planet divided by r squared. So now we have a problem here, because we have dv, dt, and here it's just distance r. We don't have, we cannot split the variables because r is not a constant. R is a function also of time. And in order to overcome this problem, we need to do the following thing. Let's say we have dv over dt. Let's us multiply and divide it by dr. So nothing will change because dr over dr is unity, so nothing changes. But it will help us to rearrange these terms in order to get rid of time. So do you see already how we get rid of time here? Any ideas?
Maybe dr divided by dt will be equal to v.
Yeah, so we can write dv over dr, and here will be dr over dt. And that, you are right, will be dv over dr times v. Okay, now you see that we don't have time anymore in this case, and we can substitute it here instead of dv over dt. So let us write it down. So it will be divided here. Like v times dv over dr is equal to minus g times mass of the planet divided by r squared. So, okay, at this point, we are done. And now we can rearrange, separate the variables, and we will get the following. So it will be v times dv is equal to minus gm. These are constants. Will be dr divided by r squared. And since we already have this separated variables, we can integrate from left and right side. So after integration, we will get v squared divided by 2 equal minus g times m, and here will be minus 1 over r, minus 1 over r. And of course, we don't forget about constant. So this constant, which is like sum of two constants which originate from both integrals. So we have this equation with some constant, and we need to apply some boundary condition in order to determine this constant. So which boundary condition would be convenient to apply here? Any ideas? What do we know initially? It's actually conditions are the same as from initial conditions are the same as for the previous case. We knew from the beginning that there is some initial velocity when the projectile is located on the surface of the planet. Means if this r is equal to capital R, the radius of the planet, then we know that velocity is equal to initial velocity. So now we can apply this boundary condition in order to determine the constant, the unknown constant. So it will be V initial square divided by 2 is equal. So here we can cancel this minus and minus. So there is plus G times M divided by R. So we substitute instead of small r, capital R. And that also, don't forget about this constant. From this equation, we can express the constant. Constant will be equal to 1 half of V initial square minus G times mass of the planet divided by its radius. So now we have the value for our constant. We can substitute it instead of this constant in the previous equation. So let us do it on the next slide. So will be 1 half V squared equal to G M over R. No. First we write small r. Then we have plus constant. Let's keep it, like take it in parentheses. So it will be 1 half V initial square minus G M divided by radius of the planet. And now we can rearrange all this in order to group the similar terms. So it will be 1 half of V initial square minus G times M 1 over R minus 1 over small r. Okay. So as a result, we can express the velocity. So we will get finally the equation which gives us velocity as a function of distance from the radius, from the center of the planet. So that will be equal to, so here 2 and 2 will cancel out. So it will be square root of V initial square minus 2 G M 1 over R minus 1 over R small. Okay, so this is the expression for velocity of the projectile as a function of distance from the center of the planet. Now we again need to consider some condition which is of our interest when it's enough to have, so the projectile is provided enough high initial velocity in order to leave the planet and never come back. So again, we can set this condition that radius, like distance from the center, should approach infinity. And in that case, we also set condition that this velocity as a function of distance should be either equal or larger 0. Because if it's going to be negative, it means that the object will start to come back to the planet. So we don't want this, and that's why the velocity should always remain larger or equal to 0. So in this case, if in addition we consider that distance approaches 0, then from this expression under the square root, we can see that in order to satisfy this condition, V initial square minus 2g times m divided by r. So we don't write this 1 over small r, because we assume that small r approaches to infinity, so 1 over small r approaches to 0. So this difference between vi square minus 2gm divided by r should always be larger or equal 0 in order to satisfy this condition for the velocity. And if, let's say, consider the minimum velocity we need, so when this is equal to 0, it will be the following. V initial square will be equal to 2gm divided by r. And from here, we can show that minimum escape initial velocity, which is escape velocity for a projectile, will be equal to square root of 2g times m divided by radius of the planet, which is the same expression what we got previously, if we can go back, for escape velocity based on the conservation of total mechanical energy, which shows how useful it can be in certain cases, because definitely it was much easier and way more straightforward to get this expression by applying the conservation of total mechanical energy. However, now you can see how it's possible to get this parameter not only based on conservation of energy principle, but also using differential equation when you get expression of velocity as a function of position, and then setting certain condition which will require to be true in order to leave the planet. Then you can calculate the escape velocity. Okay, so with this, I think this is with this calculation, the derivation part, we are done. Now we can discuss a little bit about this escape velocity. So it is definitely a function, as you may see, of properties of the planet. So we have mass in the numerator and radius of the planet in denominator. So for planet Earth, this escape velocity for planet Earth is something about 11.2 kilometers per second. If we consider Moon, that will be much smaller, it will be 2.3 kilometers per second. And for instance, if we consider a planet like Jupiter, which is the biggest and heaviest planet in solar system, that will be 60 kilometers per second. And can imagine that if, for instance, which is very unlikely, but just imagine such situation, if the mass and radius, but here mass plays the biggest role. If the mass of our planet would be comparable to Jupiter, and that would require 60 kilometers per second as escape velocity, most likely we would not be in space for very long time, because capabilities of rocket engines and this chemical fuel which we use currently, this principle of propulsion motion would be just physically not efficient enough to reach such escape velocities with some useful load besides only the fuel. So that's why the fact that our mass of our planet is not too big allowed to use this technology, which is still currently used. There's nothing fundamentally new developed, even after so many decades since the first human being was sent to the space. That would really limit our options to send satellites and explore space around us. So that's quite interesting moment, which could really change our history and our development as a civilization. But there are objects definitely much heavier than planets. And if we consider some stars, for instance, specifically the development of stars, their evolution, so depends on the mass, initial mass of the star. There is some very rough gradation. So if the mass is smaller than 1.4 mass of our sun, then in the process of burning this hydrogen and converting it to alpha particles like helium during the thermonuclear reaction in the core of the star, the fuel will be burned and the star will just turn into a white dwarf star, which will slowly cool down. However, if mass is larger, of the initial mass of the star is larger than 1.4 mass of the sun. So obviously, since mass of the sun is 1.0 mass of the sun, we are below this threshold. So that's the future of our sun is white dwarf, most likely. However, if we have some massive stars which are heavier than 1.4 mass of the sun, there is a chance for explosion of supernova at the late time of its evolution. And because of huge pressure caused by this explosion, the core is densified to that extent that it happens neutronization of the matter. So in very rough description, electrons fall on protons and convert them to neutrons. So all this neutron star is just made of neutrons, and that's the reason of its name. And its density is literally density of the core of atoms. So obviously that is very heavy object, and escape velocity can be very, very high. Moreover, in some circumstances, when this mass of the initial mass of the sun is more of the star is more than 3 masses of the sun, a formation of black hole is possible. In that case, density is even higher. That creates conditions when escape velocity, escape is larger than speed of light, which is the maximum achievable speed of transferring signals in universe. And if it's true, then even photons, which represent as particles of light, cannot escape this gravity of black hole. And that's why everything what goes into so-called sphere around the black hole as event horizon with radius, so-called Schwarzschild radius. Everything what is going into this sphere around the black hole cannot come back. So there is no option to escape this gravity because escape velocity is literally higher than speed of light. So that's why it's actually called as a black hole. However, planet Earth is not so heavy, and luckily for us, so escape velocity is 11.2 kilometers per second, which allows to use current technology, propulsion technology based on chemical fuels in order to send people and satellites into the outer space. Okay. Thank you very much for attention. I think this is everything what I wanted to tell you. If you have any questions, you're welcome. If not, then I wish you good day. Prepare for the midterm. Wish you good luck with your second midterm. Be careful and read attentively the problems. Find those problems which are easier, more familiar to you, solve them first, and then proceed with more difficult problems.
All right, and the grade is going to be curved, right?
Yes, yes. So it will be based on the average performance of all students.
So wait, the average performance is taken from all of the students that are taking the Physics 161, or just from, like, for example, our our group of like?
No, it's taken for all, since we are all in the same conditions. We are all in the same boat.
Oh, okay, thank you.
Yeah, average is considered for all students taking Physics 161.
Okay, thank you.
Okay, guys, thank you for attention. Have a good day. Bye-bye.
Thank you. Goodbye.
Thank you. Goodbye.